Good morning, I'm Chiara Pigazzolo and I'm attending my last year in Liceo delle Scienze Applicate Subreva. The title of my short talk is A Lesson for the Future at sull'amianto. It may be possible to think that it would be too naive to think that the harmful effects of mineral dust on the human respiratory system is solely dependent on the physical shape of the dust particles. However, it has been this way for a very long time. There is a complex disease generation interaction between mineral dust particles and the biological system with which they are in contact. These dust particles influence the biological system via their surface properties, chemical and electrical, as well as mechanical dimensional. Scientists began studying the nature of mineral surface interfaces and their chemical reactivity over a century ago. Respectively, in 1847 and 1867, Ebelman and Dobré studied the dissolution and corrosion of minerals. In 1870s, Newbery, Ski, and Wilkinson performed some of the first work on oxidation reduction reactions at mineral solution interfaces. In these early studies, the only way to study surfaces was indirectly, that is, by observing, measuring changes in the fluid composition in contact with the surface as a function of time. However, today we have the additional resources in the form of surface and interface-sensitive spectroscopic and microscopic tools to study these processes directly. For example, it is possible to use X-ray photoelectron spectroscopy, Auger electron spectroscopy, and scanning Auger spectroscopy. What is more, some techniques generally used for bulk analysis have been adapted for surface research, including diffuse reflectance Fourier transform infrared spectroscopy, X-ray absorption spectroscopy, and transmission electron microscopy. The properties of a surface depend on its composition, atomic structure, surface genre, and microtopography. The term reactive oxygen species, ROS, is defined by the US National Library of Medicine as molecules or ions performed by the incomplete one-electron reduction of oxygen. These reactive oxygen intermediates include singlet oxygen, superoxide, peroxide, hydroxyl radical, and hypochlorous acid. They contribute to the macrobicidal activity of phagocytes, regulation of signal transduction and gene expression, and the oxidative damage to nucleic acids, proteins, and lipids. 5 different mechanisms by which minerals may promote the formulation and transformation of ROS are explored. Mineral release of metal ions, metals that are released into body fluids via congruent or incongruent mineral dissolution, can act as catalysts. In this mechanism, minerals are a source of metals, but are directly involved in any of the reactions. Surface bond metal-promoted reaction, insoluble metal-containing minerals can catalyze formation of ROS from molecular oxygen. In this mechanism, the conversion of molecular oxygen takes place on the mineral surface, with the mineral surface itself, or absorbed species, acting as an electron donor. Intrinsic or mechanically induced surface defects. Defects on the mineral surface, either intrinsic to the mineral structure or generated by crushing, can react to form ROS. In this mechanism, highly reactive defects combine with water, molecular oxygen, or carbon dioxide to form ROS. Inflammatory cell-mineral interaction. Insoluble particles that deposit in the airways and alveoli of the lung may activate airway epithelial cells or macrophages as a result of binding to the cell interior. These processes can lead to production of secondary cells ROS, including hydroxyl radicals and other very reactive entities. Hence, minerals that do not promote ROS formation via the first 3 mechanisms in vitro may still show up regulation of ROS in vivo. Mineral surface sorbed compounds. Minerals may act as carriers of ROS-inducing compounds. Sorption onto aggregation of non-mineral ROS-inducing compounds with minerals can transform inert minerals into carrier. Dissolution of the carrier species into the alveolar fluid may induce formation of ROS. The mineral acts as a substrate for Ross simulant. Minerals which don't provoke the formation of Ross through the first free mechanism in vitro may, however, promote it in vivo. There are many different factors that can influence the health effects of hard materials, including intensity and duration of the exposure, the dose, exposure route, chemical conditions encountered along the exposure route, physical and chemical characteristics of the mineral, the potential microbial and other pathogens present in the mineral, biosolubility, biodurability, bioaccessibility, and bioreactivity of the material into the body fluids encountered along the various exposure routes, the body's immune response, the body's physiological processes that control absorption, distribution, metabolism, and extraction of toxicants, other confounding factors such as age, gender, genetics, personal habits, and personal socioeconomic, health, nutritional status, and dietary cofactors that may promote or counteract the toxic effects of the exposure. Thank you for your attention.